This lecture deals with the topic of resonance. By the end of this lecture, you should be able to draw various resonance structures and also understand when they're needed and what these structures mean. For more information on this topic, please see section 4.6 of your textbook. Look out for the Canvas quiz to be completed after this lecture. So we begin our discussion of resonance structures by drawing the Lewis structure of ozone, which consists of 3 oxygen atoms bonded together. So to draw this Lewis structure, we'll start off by counting our valence electrons. So 3 oxygen atoms has 18 total valence electrons. I'll connect the oxygen atoms, choose one to be the central atom, as we normally would, and then we can add in our lone pairs of electrons, again starting at the outer atoms first, and then going into the inner atoms following our rules. So we should fairly quickly come up with this Lewis structure. This now represents all 18 of our total valence electrons, all 3 oxygen atoms. So now when we look at our Lewis structure, we need to check to make sure all of our second period atoms have the full octet of electrons. And what we see is that central oxygen only has 6 electrons around it. So we need to complete the octet. And we're going to do that by forming a double bond. We've seen this before, but for the first time when we look at this structure, one of the things we see is we have the possibility of forming 2 different double bonds. And the question is, which one do we make? If we notice, we can form a double bond from either of the terminal oxygens, the left oxygen or the right oxygen. So I can start off and say, well, what if I take electrons from the leftmost oxygen, and that would give me the structure that's shown here, with a double bond from the left oxygen to the central oxygen. Alternatively, I could have taken that lone pair of electrons from the right oxygen to form the double bond, and end up with the structure on the right. So these two structures are very similar, but not quite the same because their arrangement of electrons are in fact different. So these structures, in fact, can also be related by moving the electron pairs within them. So I can move a lone pair of electrons from that right oxygen and then push a bonded pair to the terminal oxygen on the left, following those blue arrows, to get to that structure on the right. These two structures are what we refer to as resonance structures. Resonance structures are 2 Lewis structures that only differ in the arrangement of their electrons. All right, so all the atoms are in the same place, but some of the electron pairs have moved around. Whenever we draw resonance structures, as we'll see, we're going to use this format where we have a double-headed arrow in between the various resonance structures, and all of the resonance structures are put into brackets as shown. So in order to learn a little bit more about why it's important to recognize resonance structures, let's go back to some other Lewis structures and see some of the information that a Lewis structure can give us. And to start off, we're going to look at 2 molecules, hydrogen peroxide and oxygen. So hydrogen peroxide, or H2O2, the Lewis structure is shown, and then the Lewis structure of molecular oxygen is also shown. So we can define a couple terms to go with these Lewis structures. The first one I'm going to define is what's known as the bond order. So the bond order is simply how many chemical bonds are between 2 atoms. So we often just refer to this as there's a single bond, or a double bond, or a triple bond, etc. And we can look at this and say the bond order of that oxygen-oxygen bond of hydrogen peroxide is a single bond. And for molecular oxygen, O2, it's a double bond. Fairly straightforward. We could also define what's known as the bond length, and this is the distance between 2 atoms that are covalently bonded together. And we can measure this in a number of ways, but when we do this for hydrogen peroxide and oxygen, what we find is the bond length for hydrogen peroxide is 148 picometers. So those 2 oxygen atoms are 148 picometers apart, whereas in O2, with the double bond, the bond length is 121 picometers. And finally, we can define a term what's known as bond dissociation energy. This is how much energy it takes to break a bond. Remember, all bonds are forces of attraction between electrons and a nucleus, so they always take energy to break a bond. And in this case, what we're going to see is the single bond is easier to break than the double bond. So hydrogen peroxide has a bond dissociation energy of 146 kilojoules per mole, and O2 with the double bond has a bond dissociation energy of 498 kilojoules per mole. So what we're seeing here is that as we have more forces of attraction between two atoms, as we go from a single bond to a double bond or to a triple bond, the bond length decreases, more forces of attraction pulls the atoms in closer together, and the bond dissociation energy increases. Right? It's harder to break apart a double bond than it is a single bond. Right? So we're going to continue this comparison, but now let's add our ozone molecule into this mix. So we have our our hydrogen peroxide and our molecular oxygen Lewis structures. We can throw in that Lewis structure of ozone, taking note that there's now two resonance structures we need to be concerned with. So now when chemists go and look at the structure, they ask themselves, what is the bond length of the bonds in ozone? And what's the bond dissociation energy of the bonds in ozone? And what we would expect to see is that the bond length, we should have one bond length that's about 121 picometers for the double bond, and one bond length which is about 148 picometers for the single bonded oxygens. But that's not actually what we find. When we look at this, all we see is one bond length, and it's 128 picometers, and the bond dissociation energy is 364 kilojoules per mole. All right? So experimentally, both bonds in ozone are measured to be identical in length and bond energy. Right? The bonds are somewhere in between a single and a double bond. So they're not quite a single bond, and it's not quite a double bond either. What this is telling us is that the ozone actually exists as an average of its two resonance structures. One structure alone does not accurately represent the reality of the molecule. And this is the importance of the resonance structures. What we're saying is, whenever we can draw multiple resonance structures, what that really says is, this Lewis structure model of our molecule is not accurate enough. We can't use just a single structure. It's actually a bunch of structures averaged together that express what this molecule actually is. So let's try another example. We're going to draw a Lewis structure, including any possible resonance structures for the nitrate anion, so NO3-. So as we start this off, we're going to again count our valence electrons. Nitrogen will be our central atom. So we can go ahead and do that. We'll have our nitrogen, 3 oxygens bonded to our nitrogen. We should come up with a count of 24 valence electrons, 5 from the nitrogen, 6 from each oxygen, and 1 from the overall negative charge of our anion. Next, we're going to put our lone pairs of electrons around the terminal oxygens on the outside. We go ahead and do that, and we're going to end up with this structure here. So now we've accounted for all 24 valence electrons. But when we look at that structure, we see that central nitrogen does not have an octet of electrons around it. We only have 6 electron pairs to nitrogen. So what we're going to have to do is we're going to have to form a double bond between the oxygen and the nitrogen. But again, this is the case where we say which oxygen actually forms the double bond. And this is your big hint for when you should be able to recognize a possibility of having resonance structures. When you have multiple atoms that could each form the double bond with another atom, that's a big tip-off that you're going to have to draw some resonance structures. So we can go ahead and draw them by going through them sequentially. We'll start off with the top atom. So imagine if we move those electron pairs down to form the double bond, we'd end up with a nitrogen-oxygen double bond to that top oxygen. Alternatively, we can go from the left oxygen to form a nitrogen-oxygen double bond, or we can go from that rightmost oxygen to form a double bond. So we have 3 possibilities of resonance structures. So to finish off our Lewis structure now, what we need to do is put our double-headed arrows in between all of our resonance structures, put all of our resonance structures in brackets as shown, and don't forget the total anion has a negative charge, so we're going to put that negative charge outside our brackets. So now notice the correct Lewis structure for the nitrite anion actually involves drawing three different structures and recognizing that they are resonance structures of each other. So that's our brief overview of how to draw resonance structures and a little bit about the importance of a resonance structure. What we still have to look at, and what we'll look at soon, is how do we evaluate Lewis structures when there's more than one inequivalent resonance structures? How do we know which is the best? And on some of the molecules, when they have a charge, like that nitrite anion we just looked at, where is that charge actually located on the molecule? So we can look forward to seeing that soon. So again, please look at section 4.6 of your textbook and complete the short Canvas quiz after this lecture.